Hello students, today we are going to talk about section 7.2, ionic bonds and ionic compounds. The objectives: explain the electrical charge of an ionic compound, describe three properties of ionic compounds. In this section we will answer the following questions: what is an electrical charge on an ionic compound, and what are the three properties of ionic compounds? So when we talk about an ionic compound is a compound made up of metals, and here we have the metals, and a nonmetal. Okay, metals and nonmetals. Composed of cations and anions, remember, composed of metal cations and nonmetal anions. Although they are composed of ions, ionic compounds are electrically neutral. Okay, they are neutral. The total positive charge of the cations equals the total negative charge of the anions. For example, sodium chloride. We have sodium chloride, we have sodium, which loses one electron, so it has a +1 charge. Chlorine gains that electron and it has a -1 charge. Again, here if we look, we would have sodium and chlorine. Metal, here's the metal, and here's the nonmetal. Here's the metal and nonmetal. So the formation of positive ions and of negative ions are simultaneous and interdependent. An ionic compound is the result of the transfer of electrons from one set of atoms to another set of atoms. Ionic compounds consist entirely of ions. Consists of ions. They are not sharing electrons. We have an electron or electrons being transferred. An ionic bond. Ionic bond. This is the electrostatic forces that hold ions together in an ionic compound. And if we notice here, we have pluses and minuses, minus plus. We have a plus surrounded by negative charge, a positive ion surrounded by negative charge, a negative charge surrounded by positive charges. So it's that plus and minus attraction that holds these ions together. And we call that electrostatic force. Look closely, we have sodium. It has one valence electron, and it loses one, and so chlorine picks up that electron. Sodium loses that electron, chlorine picks it up. Here we see it loses the 3s1, chlorine picks it up, and 3p5 becomes 6. So we have a plus here, positive ion, and a negative ion. And notice the sodium has the same electron configuration as neon. Chlorine has the same electron configuration as argon. Ions like to have the electron configuration of a noble gas, and that's why they either lose or gain electrons, so they have those 8 valence electrons. So if we look at aluminum, aluminum is in group 3A. Aluminum is in group 3A. And let me just write that on the board here. It's in group 3A. It has 3 valence electrons, and it will tend to lose those electrons. And so then aluminum will have a +3 charge. Chlorine has 7 electrons, and each chlorine will gain 1. So if aluminum is losing 3, and chlorine only has a spot for 1, we're going to need 3 chlorines to pick up those 3 electrons. So we have those 3 chlorines picking up each electron from the aluminum. And so therefore we have the formula AlCl3. Aluminum has a +3 charge, and if we put it kind of on a little seesaw, each chlorine is a -1, the total net charge has to equal 0. Here we have plus 3, here we have minus 3. If we add these up, it equals 0. Okay, so aluminum loses 3 electrons, and each chlorine would gain. If we just had one chlorine, there's only one parking spot for an electron, and we have 2 electrons that are looking for parking spots. That's why we would need, let's say, 2 more chlorines. A chemical formula shows the type and number of atoms in the smallest representative unit of a substance. Ionic compounds exist as a collection of positively and negatively charged ions arranged in repeating pattern. So when we really don't use the term chemical formula when we're talking about ionic compounds. We use the term formula unit because we have more than, it's just the ratio of 1 to 1 or 3 to 1 or 1 to 3, whatever the formula is. So the formula unit is the lowest whole number ratio of the ions. If we look at this picture here, we see sodium chloride is not just one sodium ion and one chloride ion. It's a whole bunch of them. But it's a 1-to-1 ratio. So that's why when we write sodium chloride, we just write NaCl. And that's the formula unit. Okay, so we would just write NaCl. It'd be 1 sodium to 1 chloride, even though we have many. If you look at this picture here, we have, many chlorines and sodiums, but for every 1 chlorine, we have 1 sodium. So each ion in the arrangement is strongly attracted to its neighbors, and repulsions are minimized. Therefore, crystalline ionic compounds are generally rigid and brittle. So they stay pretty much in that shape. Again, you have that plus and minus attraction, so they tend not to move. They stay pretty rigid, and therefore we have a crystalline compound. Forms a crystal. So let's look at a couple of examples of formula units. Magnesium is in group 2A. Okay, magnesium is in group 2A. So therefore it's going to lose 2 electrons and form Mg2+. Chlorine is in group 7A. It's going to gain 1 electron and form Cl-. So if for every 1 electron magnesium loses, it's going to need 1 chlorine. So since magnesium loses 2 electrons, it's going to need 2 chlorines. So the formula unit is MgCl2. The ratio of cations to anions is 1 to 2. For every 1 magnesium, we have 2 chlorines. And here, again, if we look at magnesium with 2 electrons, I'll just draw a little. Magnesium has 2 electrons, and chlorine has 7. One of these are going to go here, and then we'll need another chlorine. And one is going to go over here. Okay, aluminum bromide. Aluminum is in group 3A, so it's going to have a +3 charge. Bromide is in 7A, it has a -1. So again, for every aluminum ion, and here I can color code it. We'll do aluminum in red. Whoops, you're going to see that. Okay, aluminum has 3 electrons. And then bromine, we'll do 1, 2, 3. Then we'll switch. So bromine has 7. 1, 2, 3, 4, 5, 6, 7. And so here you see the aluminum ions, electrons, going to the bromine. And so we have 1 aluminum for every 3 bromines. 1 to 3. So you would have to just balance the charges. Again, when I showed that little seesaw, I had, well, let's do the seesaw for magnesium. Magnesium has a +2 charge, and each chlorine is at -1. So this is a total of a -2 plus 2. See how it adds up to 0. And here we use the electron dot structures to predict the formula of ionic compound. Formed from potassium and oxygen, and we have to name that compound. It would be potassium oxide. We say the cation name first, then the anion name. The anion name has that IDE ending. So potassium has a +1 charge. Oxygen has 6 valence electrons. It has space for 2 more. So we would need 3 of these. Each electron, I had color-coded, goes to, well, we have 2 of these rather. 2. Each electron goes to the oxygen. You see the potassium electron I have color-coded in red, and here these really should be black. Let's just color over them to make. So potassium loses 1 electron and oxygen picks it up. We need 2 potassiums for every 1 oxygen. And so we would write this as K2O, potassium oxide. We named the cation first. The cation name is just the regular name, and then the anion second. The anion has that IDE ending. Here's some other examples. Here, use the electron dot structures to predict the formula of the ionic compound formed from magnesium and nitrogen. So let's look at where they are in the periodic table. Magnesium is in group 2A, so it's going to lose 2 electrons. Nitrogen is in group 5A. It has 5 valence electrons. So here magnesium is in group 2A. We have 2 valence electrons. Nitrogen 5A, we have 2, 3, 4, 5 valence electrons. Well, it's not a simple 1 to 1 or 1 to 2 or 1 to 3. Magnesium loses 1 here and loses 1 here. We still have an extra parking space for this one. So if we get another magnesium, that would go here. But then, and this one go here, and we still need 2 more. So for every 3 magnesiums, we need 2 nitrogens. And here we can see this. We have a total of 6 red dots. And nitrogen would pick up 3 each to get the 5. I mean, to get the 8 electrons. If we draw my little seesaw, we have magnesium has a +2 charge. And we would need, so that would be a total of +4. We would need 3 of them. Mg, okay, that'd be +6. And we would need 3 nitrogens. 2 nitrogens, 3 minus, 3 minus. That would be -6. Okay, so here we would have magnesium would be a +6, nitrogen would be a -6. Okay, 3 magnesiums, 2, 4, 6, have a +6 charge. And then we have 2 nitrogens. Each nitrogen is a -3 charge. Each nitrogen picked up 3 electrons. And so that would be a -6. +6 and -6 equals 0. Again, here we see each magnesium lost 2 electrons, and each nitrogen picked up 3. So it's not a complete 2 to 1 or 3 to 1. And here we have it. For every 3 magnesiums, we need 2 nitrogens. So it's Mg3 and 2. And here we see that. Okay, so the magnesium loses 2 electrons. Each magnesium loses. Each nitrogen gains 3. And so we have to kind of calculate how many magnesiums and how many nitrogens we need for a compound to form. A compound has to have a total net charge of 0. Total net charge is 0. So here we have an example, and I'll do this. Write the correct chemical formula for the compound formed from the pair of ions. What you could do is pause it and try it yourself, and then hit play. Okay, I assumed you hit play. We have calcium has a +2 charge. Chlorine has a -1. So for every calcium, we're going to need 2 chlorines. So it would be CaCl2, calcium chloride. And I use the IDE ending. And if I was to draw my little thing, we have calcium as a +2. We're going to need 2 chlorines for it to balance out. -2 +2. And here we have names now. Before I gave you the ions, here we have names. So we have to do a little more work. Potassium is in group 1A. Okay, potassium is in group 1A. Iodine is in group 7A. So potassium has a +1 charge. Iodine would have a -1. So potassium iodide, it's a 1-to-1 Ki. Calcium is in group 2A. Bromine is in group 7A. Calcium 2A, it has a +2 charge. Bromine is in 7A, it's going to gain 1 electron. So here we're going to need 2 bromines for every 1 calcium. So calcium bromide would be CaBr2. And again, if we look at this, Ca is a +2 charge, and we have bromide is a minus. I need 2 of those for a -2. Notice they add up to 0. Ionic compounds are usually solid crystals at room temperature. The ions are arranged in repeating three-dimensional patterns. We have a large attractive forces that results in a very stable crystal. They're very stable. Ionic melting points then generally have high melting points. Okay, so one of the characteristics is they have high melting points. They form a repeating three-dimensional pattern, it's a crystal, and they're very stable. If we look at sodium chloride, sodium is surrounded by 6 chlorine ions, and chlorine is surrounded by 6 sodium. If we look here in the center, we have top and bottom, front and back, and like left to right. So that's how you get the 6. If we look at this one in the middle here, see if I can see all of them. Here we're looking at this one. Here we have this one, top and bottom, front and back. That's 4, and kind of left and right. That's 6. Coordination number. Coordination number of an ion is the number of ions of opposite charge that surround the ion in a crystal. For example, sodium chloride has a coordination number of 6, and chlorine has a coordination number of 6. Again, here you can see it. We have 1, 2, 3, 4, 5, 6. Top, front and back, top and bottom, front and back, left and right. And we have chlorine ions would be the green, the red is the sodium ions. Cesium chloride. The internal structure is different than sodium chloride. Cesium is surrounded by 8 chloride ions, and the chloride ion is surrounded by 8 cesium. So the anion and cation in cesium chloride each have a coordination number of 8. And usually you're told this. Usually you can't just look at the formula and determine the coordination number. And here you see cesium and you see the 8. the way the structure is. 2, 4, 6, 8. This is like in the center of a cube. Titanium dioxide is surrounded, each titanium is surrounded by 6 oxygen. So titanium with the +4 charge has a coordination number of 6. The anion, the oxygen, is surrounded by 3 titanium, so the oxygen has a coordination number of 3. And here you can see an example. Titanium is surrounded by 6 oxygens. 1, 2, 3, 4, 5, 6. And let's see if we can find. Here is oxygen is surrounded by 3. 1, 2, 3. And again, usually you're told this information. You just can't look at this and know the coordination number. So, properties of ionic compounds. Ionic compounds can conduct an electric current when melted or dissolved in water. When it's melted, the orderly crystal structure breaks down. If a voltage is applied across the molten mass, the cations migrate freely to one electrode and the anions migrate freely to the other. The ionic movement produces a flow of electricity between the electrodes. Again, when you break something down, you have a cation and an anion, and it breaks apart. You have pluses floating around and minuses floating around. Cations floating around and anions floating around. So here we see a picture, and we have a negative electrode here, positive electrode here. We have salt dissolved in water. Well, the salt is broken up into the sodium ions and the chlorine ions. And so here we have the sodium ions, their pluses are attracted to the minus, where the chloride ions, they have a negative charge, they're attracted to the positive electrode. And you can get those electrons. Remember, a current is a flow of electrons. And so now you can have these electrons flow through here. So you can have an electrode here and here, and you can still have a current flow through. Properties of ionic compounds. The crystal is rigid because it's held together by a specific three-dimensional array of relatively strong attractive forces. So here we see that crystal lattice of sodium chloride. We have the negative holding on to all the positives, and we have the positive holding on to all the negatives. So it's pretty strong. And if you move them, the like charges repel. If I would push this down and have 2 negative charges next to each other and 2 positive charges, if I would take a hammer and hit it and break the lattice structure, the 2 negatives would repel each other and 2 positives would repel each other. That's why when you hammer salt, it breaks into a whole bunch of pieces. It doesn't get flat. Because when you hammer something and you change this crystal structure by pushing 2 negatives down, let's say if I would move that down, let's just draw a picture there. If I would move this down, and so now I would have a chlorine here, a sodium here, another chlorine here. We would have 2 negatives together, 2 positives together, and that's what causes a crystal to break. So the crystal is brittle because the attractive interactions are specifically arranged within the crystal structure. Again, here's just another picture of the structure. If the arrangement is disturbed, the charge repulsion between the ions of the same charge, that's supposed to be charge, can force the crystal, should be a Y there, crystal to fragment. Again, if I would make these 2 positives here and a negative here, if I kind of push this down, it causes it to break. Monatomic. A monatomic ion is an ion formed from a single atom. Examples of monatomic ions: fluorine, chloride, bromide, iodide. Here you see just one element. Oxide, sulfide, these are monatomic. Polyatomic are two or more tightly bound atoms that carries a charge. So polyatomic, and we'll deal with that in another chapter more. Here are examples of polyatomic. Notice there's more than one. Here's sulfate, carbonate, phosphate. They are more than one atom that are bound together. It acts as a gang. They travel together. And here I have these blocked out in the red. Monatomic, an ion formed by a single atom. Here we have single atoms here. Polyatomic is they act as a gang, but they act as one unit, and they have a charge. So, although they are composed of ions, ionic compounds are electrically neutral. Okay, they are electrically neutral. The ionic compounds are usually solid crystals at room temperature, and they generally have high melting points. The ionic compound can conduct an electric current. Okay, conduct an electric current when melted or dissolved in water. Okay, so I would suggest you read section 7.2, pages 194 through 199.